Welcome everyone to another OCP Tap call. This is call number 139. And today we have Karen from Meinberg. So please join me welcoming Karen as today's OCP Tap presenter. Karen is a seasoned engineer with Meinberg USA, where she focuses on network time synchronization and cybersecurity with a diverse background spanning both the public and private sector. She has held roles including network engineer, research analyst, and network sync technologist. A longtime leader in standard development, Karen currently serves as the co-chair of the IETF and PTP working group and the chair for the IEEE 1588 Security Subcommittee. Her work plays a pivotal role in driving forward the security and resilience of time synchronization protocols, particularly NTP and PTP. We're honored to have her with us today. So with no further ado, Karen, the floor is yours.
Thank you, Ahmad. Everybody can see my slides, correct?
Yes.
Okay, excellent. So from the time that Ahmad asked me to do this, I have narrowed the scope quite a bit. I started out with the title Advances in Time Security, and then I wanted to make sure that we clarified it was network time security. And then the more I dug into it, the more I thought we would just focus on the standardization parts today and possibly have some later talks by some of the experts on specific topics going forward. As Ahmad mentioned, I worked in the for the U.S. Navy for a number of years doing real-time systems. And then I worked with the Internet Society at the sort of intersection of policy and technology and deployment. And I am recently supported by Meinberg to continue doing standardization work. So for today, I'm really going to focus on what started all of this was at WSTS back in May. A couple of different presenters talked about security solutions being in draft status. And I'm like, well, there's a number of solutions that are already published. And so I thought it was kind of time to do an update on what the current status of what was published was and what is ongoing. And so this is looking across 1588 and IETF NTP working group. Just as a side note, if any of you all were following or were aware of the TikTok working group in the IETF, with the completion of the enterprise profile, that working group has been closed. And if you carefully read the updated charter for the NTP working group, it is now Network Time Protocols with an S. And so any of the time-related protocol work in the IETF is now being done in that working group. And looking across the list of people that are here, I recognize a number of you, so some of this is going to be very familiar. So my apologies in advance for potentially covering stuff you already know. So first of all, from a motivation perspective, where do security issues come from? There's really three primary sources of security problems, and that is flaws in configuration and implementation. So things like bugs and not using good configuration practices, weaknesses in the protocol itself that make it vulnerable to things like denial of service attacks and those kinds of things. And then the lack of an adequate security mechanism. And a lot of times when we're talking, we're thinking about the security mechanism, but addressing those first two items is also very important. So I've gone ahead and included the standards work and documents in here that address those first two issues as well. So prior to 2020, in IEEE 1588, 2008, we had Annex K, and Annex K was defined as experimental at the time, and there were a number of flaws identified with it. It did provide group source authentication and message integrity. It also protected against replay attacks, but it did have a number of flaws, and it was never really adopted from that standpoint. And then NTP and the IETF 5905 brought forward this symmetric key authentication scheme from NTP v3. It had the optional MAC and it had a pre-shared key scheme for server authentication. In addition to that, there was, and that was a standards track document. In addition to that, there was 5906, which was AutoKey, and it used authentication of time servers using PKI. This also had a number of known flaws, and in fact, the security community in the IETF was opposed to the publication of this as a standards track document, and as a result, it was published as informational. And it has concerns about design and some limited deployment. So prior to all of the updated standardization work kicking off, we had an effort in the TikTok working group at the time that was looking for requirements for time security, network time security. And this was published all the way back in October of 2014. It did a requirements and threat analysis for both NTP and PTP. And this was a document that was used by both the IEEE and IETF in the development of their security solutions. It's done a pretty decent job of standing the test of time. There are some things that at the time we thought would be less important that have sort of come into the fore and been deemed as more important. But that is one of the foundational documents for defining the requirements for both the security work in IEEE and in IETF. So moving on to 1588, the current status of published security work in IEEE 1588 is the current core specification 2019, and then it was amended by 1588D, which added additional information on GDOI key management. I'll get to it a little bit later, but GDOI is used primarily used fairly heavily in the power automation industry, and there's a IEC standard that references this as well. So basically, the 1588 security approach, from the early discussions on what the requirements were, it was again sort of looking at the sources of potential problems and how people looked at solving problems. It ended up with a set of mechanisms and tools that can be used together or separately, and all of the individual mechanisms are optional, and which ones you choose might vary based on your application or your environment. It was a multi-pronged approach, and so it had four aspects to it. One was integrated security mechanism, which is built into the PTP protocol itself, so it's a security mechanism added to PTP. The second one was external transport security mechanisms. So oftentimes in a network, you will already have IPsec or MACsec as part of your overall security infrastructure, and the utilization of that can also secure PTP as one of the types of traffic that's carried there, and that's prong B. Prong C is architectural guidance, so how you design and build your network can improve the security of it. And currently, prong C deals primarily with redundancy. And then prong D, which is looking at monitoring and management and what those can do to improve your security posture. So the big piece that was the new development in the 2019 version was the definition of this authentication TLV. And so 16.14, that section, is the normative section that tells you how to implement the authentication TLV. It does not tell you the security information associated with it. It defines the fields that you can use to transport the security information. And so in conjunction with that, you're going to need some form of key management. So you can use 16.14 with static key management, but that's not very scalable. And so Annex P, which was the informative annex, provided some introductory information on GDOI and Tesla as potential key management schemes. And then the 2023 1588D, that amendment provided a lot more information on details on exactly how you could use GDOI. And then that's the material that was referenced in the power industry. So this is just the packet format of a PTP packet with the authentication TLVs put in. You will note here that there can potentially be two authentication TLVs, because one has to do with supports immediate processing, and one supports delayed processing. And so you can use the immediate processing one to actually secure the distribution of your delayed processing TLVs. So what's the difference in immediate versus delayed? So immediate security processing processes the authentication TLV before the contents of the PTP packet can be used anymore. So basically you have to have all of the security parameters in order to calculate the ICB. What delayed security processing enables you to do is it creates sort of a sliding window. And so you can continue to process the data in the PTP, but you can look backwards, and that allows you to separate the security processing from the PTP packet processing, and then you can roll back a tiny bit. And so depending on your application, you may or may not be able to use this. So GDOI, for example, requires immediate security processing, and Tesla was an example of delayed security processing. The two can be used in conjunction. The other thing that you're going to be looking at is what other security mechanisms are being implemented in your system, because you don't want to build a big security infrastructure to support PTP. PTP is going to be a piece of a broader system. So this is the new authentication TLV that was defined in the 2019 version. You can see the security parameter pointer and the security parameter indicator. You also have some optional fields there. Those optional fields are the ones that some ongoing work is continuing with, in particular the sequence number and the reserved field. And depending on the key management scheme that you use, you may put different things in these various fields, and that's where the additional specification is required. So you can do some static key distribution with some form of out-of-band mechanism. It's good for getting started, but it's not really a long-term solution. What's currently in the document is a lot of detail on GDOI, some general ideas on Tesla, and then separate from that, we're going to be working on an NTS update for key management. I'll talk about this a little bit more later, but one of the reasons why we're interested in NTS is it's, a lot of servers have both NTS and PTP. And so we would like to have as much commonality between the solutions as we can. And so we're looking at coordinating NTS between NTP and PTP, and then potentially CS-PTP. So this is sort of an abstract view of GDOI. So you have a key distribution center, and it's delivering these traffic encryption keys to the group members. And each key, the key is the same for all of the group members. So the key here is that the maintenance of the group becomes very important. And so everybody has the same key, so you need to control I just lost the word, but the correctness of the group. So if something gets corrupted, then you need to redistribute a new key to everybody. So in this case, the way the immediate key sharing works is the key distribution center distributes the key to each one of the instances. And then after all of those have been distributed, then the PDP data exchange can start using the key that was distributed, and it can be used to calculate the ICD in the TLV. The difference with delayed key sharing in Tesla, and this is not the best picture to show what I'm trying to illustrate here, but basically you have a sliding window where you're sending updated information, but you have a window over which you can go back if you need to. So that is the point of this. It makes it easier, so it makes it so that everybody doesn't have to have the same key, but or not everybody knows the same key, but the keys are distributed to the members individually, and you have a sliding window that gives you an opportunity to update them. This is, to my knowledge, not yet really being used. I think it really needs some more development. The annex is fairly light on that. For the rest of the prongs that are in the 2019 version, there are details on how to use that MACsec or IPsec. And again, this is really, if you're already using this infrastructure in general for your security system, then you can use that and potentially not need an additional mechanism in PTP. The same groups that are using the GDOI are also doing a lot of the MACsec work. Finally, the guidance for prongs C and prongs D. The architecture guidance provides for the redundancy that I mentioned earlier, and then monitoring and management guidance is the parameters that can be monitored to detect security problems. In the current version, the parameters that are discussed are PTP parameters, not necessarily security parameters. And one of the things that you'll see in the PAR for the new work ongoing is that we haven't really defined data sets to represent the security aspects yet. So that will be part of the work that's being done in the latest update. And then also there was a recommendation to not use like the old 1588 native management. So that's all published and available and ready for people to start, or some people have already, some implementations are already ongoing. I'll talk a little bit later, but this is the point where it would be really helpful to get some feedback on how, what is working and what isn't working and what improvements are needed. We've already found some gaps that are being addressed in the current open PAR related to this work. So the next thing is the network time security protocol that was developed in the IETF. Now, this is RFC 8915, and it was published in September of 2020. There are multiple interoperable implementations now. There's a number of open source implementations. There's also commercial product support. There are some public NTS enabled NTP servers. These are really at this stage experimental in the sense that we don't have something analogous to like the pools.ntp.org to support it. But there are, I know Cloudflare and NetNode, and there's a few others that have put up public NTS servers for NTP. So it provides integrity for the packets, unlinkability, provided you're using the data minimization techniques, authentication of servers, and a request response consistency to help avoid replay attacks. One of the current issues that we're having in 1588 is beefing up the work that we did previously on addressing replay attacks. So here are the components of NTS. There is the NTS key exchange server, the NTP server, and the NTP/NTS client. One thing to note here is the NTP server and the key exchange server could be the same device, or they might be separate. You might have a single key exchange server or a couple of them that are serving any number of NTP servers. One of the things that's not been specified yet, which there's been some talk about doing, is specifying the interface between the NTP server and the NTS key exchange server. So right now it's implementation dependent, but we would like to specify that in such a way, with the thought being that that NTS key exchange server looks a lot like the key distribution center on the PTP side, and potentially that's where we could get some commonality. And so that a single key server could service both NTP and PTP type clients. Anyway, the key exchange server provides the information to the server and the client that it needs, and then the authenticated messages can go between a server and a client like they currently do using extension fields. So one of the things in the development of NTS, we started out basically with a roll your own approach, and then the security community strongly encouraged the NTP community to look at TLS. And so this is the key exchange piece of it is done over TLS. So you set up all the key information that you need, and you close down the session, and then you start with your normal time synchronization over NTP. And so once the client has the information with the extension fields, then the server can generate responses based on that information. And then if you need to re-establish the security association, then you go back to the TLS connection. So here's a few links to some NTS information that I thought might be particularly useful. Martin Langer did one of the earlier implementations of NTS, and he wrote a really nice detailed blog post on that. There's also a NetNode white paper. NetNode was heavily involved in the development of NTS, and they also stood up a commercial server or a public server. And additionally, they were looking at the development of this in hardware to support their time project for their national infrastructure. And then I just doing a random look on the internet, I found a few sort of company articles related to NTS that I thought might be useful. So those are the two big ones, the 1588 security piece and the NTS piece from IETF. There are some other related standards updates that since I was in the process of doing what's going on in standards related to security, I thought I would go ahead and provide these. First one is the updated MAC for NTP v4. This one is a little bit of a no-brainer. It basically replaces MD5 with AES CMAC. In 5905, it was something that had needed to be done for a while. The other thing, if you are following IETF RFCs, you can see that the change in format of RFCs in the PDF formats going forward. This is the NTP best practices document. I said early on that a primary cause of issues with security is often just not configuring it correctly for the environment that you're operating in. And this is a set of best practices for NTP. Some of this analogous type of information is what's intended by Annex P in the 1588 documents. Next is a port randomization RFC. And this allows you, instead of being on port 123 the whole time, it allows you to do some port randomization, and that helps to reduce, if you don't have to be on port 123, this helps to reduce, in particular, a lot of denial of service attacks. And then Kronos, this was debated to be experimental or standards track. It did end up in the end on, oh, you know what? I put the wrong picture there. Oh, look at that. KONOS is an informational document, and it's RFC 9523. Guess I did a cut and paste wrong. So RFC 9523 is a mechanism that allows you to do, it sort of is a external mechanism to NTP that watches over the NTP servers and filters them as for correctness to make sure that you don't have any intentionally misbehaving servers. There was some effort by the Network Time Foundation to implement this. I'm not sure of the status of that effort. And there's a couple of academic papers written on it as well. Ignore the picture. So those are some other things that have been completed in the last 5 years. And so then next is what's going on now. Well, I don't know that this is necessarily of particular interest to this community, but Rough Time is a document that's been in progress now for 4 or 5 years. And it looks at authenticating sort of a rough level of time synchronization. It originally came to the NTP working group from a sort of a bootstrapping perspective and to detect bad or misbehaving time servers. It can also be used in conjunction with NTP. The decision of the working group was to publish this as experimental. It has passed the NTP working group last call, and it's ready for forwarding to the IESG for the final IETF processes. The idea is that we will publish it as experimental and then come back in a few years and see if it's having the effect that it was originally desired. It came out of a lot of the community that's looking at issues around certificates and having, if you have a system that's coming up that has no idea whatsoever what the time it is, and that sort of chicken and the egg problem where how do you know if your system is, if you can establish the certificates correctly if you don't know what time it is. And so if you have any interest, I've seen there's been some discussions in some of the operator communities about how this might be useful. Provided it doesn't hit any major hiccups, it's probably going to be published by the end of this year, early next year. The second thing that's really of interest, more so to NTP than PTP, is the concept of NTS pools. One of the things that a lot of client devices come pre-configured with NTP. If you think of NTP as sort of a global internet type thing, a lot of devices come configured with their servers as pools.ntp.org, and then there's a back-end support system that does a selection of which servers are closest to you and that kind of thing. One of the problems with NTS is that you can't currently deploy it in the pools because you need to have the server has to maintain, you have to know who all of your clients are, and that's not the way. You can't authenticate to a set of servers, you have to authenticate to a server. So there is some work on an individual submission that's looking at enabling NTS for pools. There has been some initial preliminary implementation work done. This was also an effort funded by ICANN with the idea that eventually there might be NTS hosted pools as a general service, like pools.ntp.org. So I'm not sure where this is going to go ultimately, but thus far it has been warmly received in the NTP working group, and I think it has the potential to solve some important problems with respect to the deployment of NTS for NTP. And even outside of the general internet, if you are you can operate private pools as well, and this technology would be useful in that context. Having said that, it is it's just right now at the experimental stage, so we'll see where it actually ends up. The next one is the 1588K, which is the currently approved PAR for security work in the IEEE. And specifically, the items that are in this PAR are support for additional key management mechanisms. In particular, when we started down this path, we were thinking about NTS, but by the time we finished, there might be another key management mechanism that we're not aware of that somebody brings to the table. Also, updates on the existing key management mechanisms. So any updates to GDOI or Tesla that we need to do. As I indicated, I think Tesla could use some more specifications, so that would be helpful. Updates on the use of optional fields in the authentication type TLV. Basically, there's been, I think I've got another slide on this, but there have been some vulnerabilities identified with what was published, what the current standard is for 1588 with respect to security. And so we're looking to address some of those. The 1588 data sets to specifically represent modeling of the security options. In the publication the last time around, we did not get to the point of defining data sets specifically to model the security aspects. And then the ubiquitous any corrections or clarifications. So that's the work. The current work items, we have some PTP vulnerabilities that have been identified. These were identified actually by the NTP working group during the discussion of the adoption of NTS for PTP. The way the work is currently broken down, NTS, the definition of NTS is done in the IETF, and then the application of NTS to PTP would be done in the IEEE 1588 group. And in particular, we've identified a number of issues with the sequence ID, and there's a number of schemes on the table right now. And we've been making some progress, but I can't currently tell you where that's going to fall out. Contributions and participation is always welcome. And then I'm going to talk about two other things. One is NTP v5. That seems like an odd one, but one of the differences with NTP v5 versus NTP v4 is that it's going to be built with security as a foundation. So it's going to be based on NTS from the start. It is still in draft specifications. It is adopted as an NTP working group effort. We have a draft specification. We have a number of sample repositories. We've done some hackathon work on this. This, I would project, could be maybe some of the others of you on this call that are already participating in this could tell me how close I am on this, but it's potentially, we would, this could be done within the year. It might take a little bit longer. It will, it narrows the scope of NTP to server client only. And I guess I would say this in the context of both NTP and 1588. A lot of work is contribution driven. And so the people that come and provide the contributions help drive where the end result will be. And right now, the active participants in this are very interested in improving the security posture of NTP by getting rid of some of the more problematic aspects of NTP v4. And I just stuck this one in here. This is 1588.1, which is CSPTP, and I see Doug is on the call. There might be others here as well. This is a new project, relatively new in 1588, And the reason why I brought it into this context is for the same reason that I mentioned NTP v5. In both of these cases, the hope is that the security will be built in from the beginning with that approach. So this is the text from the PAR. I'm not going to read it to you, but there you have it. So the status of this is that in 1588.1, there has been a starting draft, a place to start that's been selected from multiple proposals, and discussions on that draft have started. There is a plan to incorporate security in the initial standard, and there is an initial proposal for the use of that. I wouldn't say preliminary implementation work, but there has been some hackathon project work done on this. Often at an IETF meeting the weekend before, we host hackathon activities, and this gives us an opportunity to work on implementation or interoperability type testing. It's proven very useful in getting NTS for NTP completed and out the door. And at the last IETF meeting, we did have a project that looked at NTS for CSPTP and also NTP v5. The one thing, and also in the NTS pools. So it was a very small group of people, but there was a lot of discussions and activity in that area. So that's the thing with that. The other thing I wanted to note about both about the CSPTP work and the NTS for CSPTP, the current thinking, which obviously could change because this is very preliminary, is that CSPTP, NTS for CSPTP could be a lot like NTS for NTP, and perhaps more so like that than like the NTS for PTP. So we'll see where that goes. So final remarks. We actually have accomplished quite a bit in the last 5 years. We do have some solutions that are now available to address a lot of these concerns. There is a lot more work to do to improve and expand the current solutions, but that does not mean that there's nothing there to work with now. So, what would be helpful here? It would be additional insights into what today's and tomorrow's systems require, and then also always looking for feedback and implementation and deployment experiences. If somebody tells you that there's nothing out there for security, that's not true. I feel like there's a lot out there right now, and we need more people experimenting with it and implementing it to see where the holes are and what's next. I think, as with all standards, but I think in particular with security standards, they, today's solution is tomorrow's vulnerability. So it's like you need some of the underlying assumptions that we made, in 2014, 2015 for the current security information in PTP, have subsequently, some of the constraints that we thought we had, we no longer have, and some of the assumptions that we made, people don't consider those to be valid assumptions anymore because it is definitely a changing landscape. And sort of some acknowledgments and thanks, because truth be told, I've been chairing these groups for a while, but there's a number of people who are the real experts and do most of the heavy lifting. In particular, Stefan Fries, Martin Langer, Rainier Birnbach, Doug Arnold, Miroslav, David Benhook, Dieter, and Tal Mizrahi. Those are the ones who in particular have been very helpful in the NTS and also the 1588 security updates. Of course, all of the 1588 contributors and all the NTP, NTS contributors, and all of the mistakes are mine. And that was a quick and dirty perusal of all of the updates on standards. Are there any questions?
So I have a question. So have there been some known attacks that are, you usually hear about attacks on infrastructure for different things, but are there, I think, GPS spoofing might be one way that time has been attacked, but are there any new interesting ways that time is being hacked or people are attempting to hack time?
I'm not aware of new ways that people are actually attacking time. What I'm aware of is people identifying ways that you can attack time.
Okay.
Is that a...
Yeah, no, I was just curious if, yeah, it's kind of like, you know what you know, but you don't know what you don't know.
Right.
And so we can, yeah. Okay, thank you.
Yeah.
So Karen, if I might, this is
Oh,
Doug
please.
Arnold. Two things to point out. One is there's some research that's been conducted at Marist College, sponsored by IBM, where they found all different kinds of ways to break PTP. And basically anything that wasn't protected by the Authentication TLV was easy. They also found you can do denial of service attacks without really a lot of messages. So if there was a switch that was looking to block DOS attacks, it wouldn't notice. If you just send, for example, a lot of announce messages to a PTP node, they all have to get processed at the software layer. So it doesn't really take that much. The other thing to point out is PTP might just be the most vulnerable protocol ever devised. If you're doing multicast PTP with the best master clock algorithm, because any node on the network can say, I'm the best, and give some credentials that are completely made up and take over time for the PTP domain. So it's only a matter of time before it actually happens in the wild.
Yeah, those are really good points, Doug, and I neglected to mention the Marist work. I think the challenge I was looking at was the difference between what people have proven you can do versus what people are actually doing. And in particular, thinking about David Van Hook and the stuff that he has identified, it seems that it's, people could do this, but most of the attacks I'm aware of in the wild have to do with NTP, and they're mostly like denial of service type attacks and those kinds of things, or misconfigurations that look like denial of service type attacks. But one of the things, like it seems to me, and Doug, you can speak to this as well, but things like replay protection, we didn't seem to think that was as big a concern 10, 12 years ago, and now replay protection and man-in-the-middle type attacks seem to be more at the forefront of people's minds. So I think the requirements that we're facing are changing as well.
Yeah, agreed. One other thing that might be worth pointing out is it started in the telecommunications industry, but now it's part of IEEE 1588, and that is a boundary clock that has ports that you can't synchronize that port from someone who claims to be the best master. You can it only outputs time. And so in a network, you can set a couple of ports to be ones that could be synchronized, and everything else is like, no, it's output time only. And therefore anything downstream can't take over the timing of the network. And that's actually out there. It's in the field. It's lots of manufacturers offer it. So it's one of maybe the most deployed security mechanism for PTP, and it's obviously only a partial mechanism, but it's one I always recommend.
Yeah, that's a good idea. I think one of the things is the thought early on was that the 1588 specification would define mechanisms, and then profiles might provide additional guidance on how to use those mechanisms to deal with specific threats that were of more importance in the environments that they were dealing with. And, I haven't followed all of the profile development, but I don't know if that's really come to pass or not.
Just wondering what something, I don't know, I'm pretty sure it has been looked at. Let's say if we go for PTP servers in WAN, where I mean, this is like really a lot of infrastructure has to change. Say you have a PTP server available to you via your ISP. And assuming everything in between is like some sort of a TC and there's hardware timestamping everything and so on. And we need some way of authentication because you don't want to have, let's say, I don't know, somehow an intruder. Would we be able to utilize similar things that we have like with RSA, where you have like some public and some private key and then take it from there? I mean, you mentioned something in the beginning of your presentation.
Yeah, I think the keying that's used in NTS does have the like you use public certificates to establish.
Right. Yeah.
But I think the exact details of how that might work are still to be developed.
So, hey, Karen, it's Greg. So one thing with kind of the adoption of generalized security for PTP, contrasting that with NTP, because PTP has TCs, has hardware timestamps, has mutable data. That's what I saw in your slides. Do you think there's going to be a split where, yes, you can implement security, but you're always going to have this layer of the network that's free to make changes to your packets, so that you have a kind of a capital I internet model and then more constrained solutions? Or do you think there is a one size fits all?
I definitely don't think there's a one size fits all, and I think that's what when we first started down this road, we were young and naive, and we thought we could do NTS and it would solve all of the security problems for both NTP and PTP, and that quickly did not come to pass.
All right. See, is any more questions? All right. Hearing none, I think we have also here Karen's email address. So if anyone has further questions, they can reach out to Karen, and I will post this recording with the slides on the wiki. And we thank Karen again for the very informative presentation we had today. And we look forward for everyone in 2 weeks for a call by Yuliang Lee from Google about Firefly. All right?
The one thing, Ahmed, is if there are specific topics here that you want additional details on, we could talk later about scheduling others to come and do those.
For sure, for sure. Thank you. Thank you. Thank you for that. Yes, absolutely. Yeah. All right. See everyone in 2 weeks. All right. Bye.